Pre-calculus. We are still currently on section 3.1, looking at symmetry and coordinate graphs. We have already taken notes on point symmetry. We've learned how to take a look at the picture and tell by rotating it 180 degrees about a certain point if it does have point symmetry. We've also looked at how to test for point symmetry or origin symmetry using algebra technique. So like f of negative x is equal to negative f of x. We've looked at line symmetry and what that means. There are 4 types of lines that I want you to focus on, 4 types of line symmetry. That would be the x-axis, which is horizontal, the y-axis, vertical, y equals x, which is a diagonal rising line, and y equals negative x, which is a diagonal falling line. We've looked at how to do those graphically, and we're currently getting ready to do this algebraically. So this is where your new notes begin. You can put it on the same page. Again, today's target is how do we find line symmetry, test for symmetry. So we're doing algebra. Again, there's common lines, and those are x-axis, y-axis, y equals x, and y equals negative x. You do need to copy everything down, including the table. For line symmetry to be x-axis, this is what needs to be shown. First, the x-axis, which is the horizontal one, is here. You need to imagine that dashed line. If a graph, and I think it's easier to take one point at a time, if you can find a location on the graph and then look at the ordered pair for that, there's some location there, x comma y, whatever that may be. If it has line symmetry about the x-axis, then what's going to happen is it's going to reflect or flip to the 4th quadrant. It's going to land here. In order to land there, there is one change. Again, if the ordered pair is x comma y and you've reflected it from the 1st quadrant to the 4th quadrant, the only thing that's changed is the y value. So like for example, if this is 1, 2, let me just give you a specific example. If this ordered pair is 1, 2, and I'm asking you to reflect it across the x-axis and it land in the 4th quadrant, then that point is now going to become the same distance horizontally, so the x doesn't change, but the y does because it's in a different quadrant, and so it's going to be 1, negative 2. When you can kind of picture this scenario in your head, then this will make more sense. So that's my suggestion. Every time they're asking you to do x-axis line symmetry, picture in your head that you're actually just at one point going from like the 1st quadrant to the 4th quadrant, and the only sign change that happens or needs to happen is that the y value changes to a negative. So saying that, you're going to substitute the x, whatever that number is, you're going to keep it the same. You're going to substitute the opposite of the y value from the original. So we're going to substitute x in place of x and negative y in place of y into the equation to see if it's equal. Secondly, to have or to prove a y-axis line symmetry, you do have to, I suggest, focus on one point. So we'll start in the 1st quadrant. About the y-axis, again, is the vertical line symmetry, shown in yellow here. If I am to reflect or flip across the y-axis, then this location is going to land in the 2nd quadrant. Whatever this ordered pair is, this one's going to be similar. For example, if this one is, let's say 2, 2, and I'm reflecting it across the y-axis, then the location obviously has changed. Now the x, since it's in the 1st quadrant, is negative, but the y value is still vertically the same distance from the y-axis or from the x-axis, so it should stay the same. Therefore, you're going to substitute an opposite x, a negative x, into your equation. You're going to substitute y into y because you can see the y's don't change. And then you're going to see if the equation is equal. If your answer gives you the same thing back as the original problem, then that is proving that the test works and that it does have y-axis symmetry. Third, to test for y equals x symmetry, that again is the diagonal line that has a slope of 1 and goes through the origin. Your job is to locate a point, and I'm going to just choose this one in green, and now you have to picture reflected this direction. And so the location from my beginning to my end is still in the same quadrant. So my sides are not going to change, but the distance from the origin does. The distance from the origin does. So, for example, if this one is, I'm going to call it 2, 3, just as a quick example, then this one, where it lands, is going to actually be 3, 2. In order for it to be symmetrical across the y-axis, basically what happens, notice the x here becomes the y, and the y becomes the x. These points both have to be the same distance from that dashed line. So, algebraically, you're going to substitute y in place of x and x in place of y into the original equation. You're going to solve, you have to look at it algebraically, simplify it, and see if it's equal to the original. If it is, you can say yes to y equals x symmetry. If it's not, you say no. Fourth, to prove that a picture has, or an equation has symmetry across y equals negative x, this is the diagram that you should have in mind. I'm going to pick a point on the first quadrant in this little piece. I chose this point. If I reflect it across this line, it's going to actually change and move to the third quadrant. We know all ordered pairs in the first quadrant have positive x's and positive y's. When it reflects and lands in the third quadrant, all of these points have negative x's and negative y's. Another thing that we've got to remember is not only does the sign, or do the signs change, but also the distance from the origin. So, algebraically, you're going to have to substitute the negative y into the x in the problem, and a negative x in for y in the problem, and solve and see if it's equal. Example, determine whether the graphs of the following equations are symmetrical to the x-axis, the y-axis, y equals x, y equals negative x, or none. Determine whether the graphs of the following equations are symmetrical. We've got all line symmetry. Notice that. Since it did ask us to determine whether the graph of the following equations are symmetrical, we actually could do either method. We could do it graphically, meaning that if we're using our graphing calculator, and we probably need to move through some of these messy equations that you're going to see in this section, I would solve all my problems for y. As soon as you solve it for y correctly, you're going to go to your graphing calculator. And if you don't have a graphing calculator, this is the part of pre-cal that you really need one, then you're going to have to use your laptop or a app on your phone or something like that to help you with the graphing part. You're going to need to know what the graph of this looks like, and I'm just going to give you a rough sketch. Not going to be perfect here, just so we have an idea. It's going to look similar to this, for example. Okay, so I'm doing the graphic approach first. I have to answer the question, does my green graph, or is my green graph symmetrical across the x-axis? And on that one, I would do what I did in the last assignment. I want you to write it out so that way there's no confusion and I know exactly which part you're answering. For x-axis symmetry, your answer should be no. Now you move to, does this graph have y-axis line symmetry? If it does, then it should be able to be reflected across the y-axis. So, does this piece fold onto this piece? And the answer is yes for that. Third, you're going to go with y equals negative x. Sorry about that. That line's a little crooked. But it should have a slope of 1. I continue to remind you of that. So you can't draw just any old line. And again, I'm doing that just for a quick sketch. But on graph paper, you would make sure your line has a slope of 1 and an intercept of 0. And you will have to use graph paper for your assignment. This piece will not reflect over here. It doesn't even land in that same location. So that would be a no. You'll do the same thing for the last one, which is the y equals negative x. Again, it's the one that has a slope of negative 1 and b of 0. In order for it to actually work, this piece would have to reflect over and land on top of itself, and it's definitely not going to do that. Or it looks like it's not. We'll put it that way. Okay. So again, what I have done so far on example 1 is I have shown work and used a graphing calculator, and I've done the graphic approach. Okay, now we're going to have to do the algebraic approach. And the reason being you need to know both is because sometimes some equations that you're given are really hard to solve for y, and even using the calculator, sometimes it's hard to tell if the graph is symmetric just from your screen. So this gives us a safe proof way of finding the answer and knowing without a doubt, and trying to avoid like technical issues with the calculator. So this is a great approach, don't get me wrong, use it when you can, but sometimes graphs or equations are a little hairy and they're hard to graph, and so this is a good way to do it. Okay, so kind of keep that in mind. That's why we have to know both. Alright, so we're going to start with, and again, I want you to be organized, because if I can't figure out which piece it is, then I can't score it for you. So we're going to be organized. We're going to list it as we're going to do x-axis first. Again, if it has x-axis symmetry, remember my comment from earlier, it's going to go from like the first quadrant to the fourth quadrant. So the only thing that's going to change is the y value. Okay, so I'm going to take this equation, I'm going to copy down, take the original problem, is what I mean by that. And you're supposed, according to your table, the notes that you took a minute ago, you're supposed to substitute x in for x, and the y value is supposed to change. Okay, so here's what you do. You take x and you put it right here for x, which basically means you're not changing that. Where you see y in your original problem, you're putting negative y in its place. Okay, I just did that. And then you can, anytime obviously you see a double sign, you can change it. So that should say like x squared minus y equals negative 3. And then you pause and you ask yourself the question, is the original equation exactly the same as the new equation? It is not. The sign has changed here. And so this one does not have x-axis symmetry. Well, we knew that from the graph. This is the algebra way proving it. Next, we'll do y-axis symmetry. Okay, to get the y-axis test, algebra test, you have to substitute. You have to remember going from the first quadrant across the y-axis to the second quadrant. And the x values are changing signs. So you're going to substitute a negative x in for x, and the y is going to stay the same. Okay, so here's how that's going to work. Again, you recopy the original problem. I would do it every time because there's a lot going on here, and it's easy to lose your place. So that would be my suggestion. You're going to put negative x in for x, but look, this one's squared. So when you write it, you need to do this, because if you don't use parentheses, it will cost you answers. You're putting a negative x in this position. You're putting y in this position. Okay, negative x quantity squared. Negative x times negative x is positive 1x squared. If I had not used parentheses there, I would have not gotten that same term. And that would have been a major problem for my answer. Notice the original problem, notice my new problem. These match exactly, which is good. So that's proving to me that this graph does have y-axis symmetry, and we can tell it from the picture, of course. Alright, I'm going to move over here because I'm running out of room. We're going to do the y equals x test for symmetry. In order for it to have y equals x symmetry, you're going from maybe this location to this location. So you're still staying in the same quadrant. And remember the notes, when you backtrack, you're going to substitute a y in for x and an x in for y. Because the signs aren't changing, but their position from the origin is the distance. And so that's why we have to kind of switch places. All right. Again, reminding you, copy the original problem down first. This is telling me right now to go, this is where normally the x coordinate is, but they want me to put y in place of x. So I'm going to show that here. Okay, so I changed this to y. Then the original problem says plus the y value. Well, the y is x in this problem, in this test, I should say. And then your job is to look at that and simplify it if you need to, or just look at it and say, is this the same equation as that one? And the answer is no. Okay. All right, last test for this problem. How do we prove or disprove that it has y equals negative x symmetry? Let's go back. That means it's going to go from maybe the first quadrant to the third quadrant, so the signs are going to change, and the position of like the distance from the origin. So we're going to substitute like negative y in for the x and negative x in for the y. There we go. And let's see what happens. Okay, we're going to put this in this place, but remember it's squared, so you're going to write it down with a negative y, and you're going to include parentheses with the power of 2, since that's what the original problem said. Then you're going to add to that the y, but the y in my case is negative x equals negative 3. I'm going to simplify this just because it needs to be, it has parentheses around it. So negative 1 times negative 1 is 1, y times y is y squared. This plus and minus is going to change to just minus. And now we make the call. Is this problem the same as this problem? And the answer is no. So, showing 4 algebra tests for this one problem. is what you'll have to do in your assignment. I will give you one equation and I'll ask you to show the test for symmetry. When I say test, I'm talking algebra. You'll need to show me the work for x-axis, the work for y-axis, y equals x, y equals negative x, and then give me 4 answers for each. Okay. All right, let's take a look at example 2 very quickly, just because it looks different. It has absolute value bars around the y, and this is a really good sample of what I was referring to earlier. When you're given a choice, and I don't tell you you have to do the graphic or you have to do the algebra approach, it's your choice which way you want to do it. But in this case scenario, doing it graphically would be difficult because obviously it has absolute value bars around the y. And so you'll have to know enough about absolute value equations to fix that problem. When it has bars around the variable, you learned from the past that that means there's 2 parts. That means the first equation is going to be everything the same behind the equal sign. But the second equation is going to be the opposite of it. You can think of it like I'm doing here. Like, notice how I'm writing this down. Okay, and so let me show you very quickly. If I've lost you right now, make it easier. If I give you this from Algebra 1 and say solve that, you could probably just do it in your head, okay? But the algebra behind it is what's helping you here, okay? So the absolute value of x is equal to 7. You were taught to write down 2 equations. The first one is the same, except just leave off the bars. And the second one is to change the sign of the term behind the equal sign. So there are 2 answers to an absolute value equation. Well, here it's the same scenario. It's just a much more advanced. We are in pre-cal. And so I'll just have to notice that, okay, I've got those bars around the y. How do I take care of that? I set up 2 problems. First, I write down the same thing. Notice this is the same. Second, notice that I have changed the sign of everything behind the equal sign. Almost. I just got to do a little bit of work. Okay, so think of that like a -1. So maybe it'd be better to write it like this, so we can see it better. -1 times 1 is -1. So what we're going to do is, and when you're on your own, you would make the call, do you want to just graph it? Well, if you want to graph it, that's okay. You need to make sure that you show me the picture on your paper. But in Y1, you would write or type in that equation into your graphing calculator. And into Y2, which is the line right underneath it, you would type in this part in your calculator. And then you would look at both pictures and you would draw that picture on your graph paper to the best of your ability. And then you would make the call, is it symmetric with respect to the x-axis, the y-axis, and the wording's different, both or neither. So because of the way I worded this one, I don't really have to do y equals x and y equals -x. So also just be careful, as always, read directions very, very closely. And that way you know what kind of work you're supposed to give me. So let's try this algebraically. If I were doing the x-axis test right now, for the second time today, I would need to remember that the y value changes signs. And so I'm going to do x common -y. I'm going to go back to the original problem here, and I'm going to copy down original problem. Okay. The only reason that I wrote 2 problems is if I'm going to have to graph it. If I choose the graphic approach, then I got to do it this way. I'm supposed to put x in place of x, where I see x, and -y in place of y. So let me do that. If I put -y here, and x in for x, which does not change anything, but I'll still write it down. I have to show it. Now I'm asked to see, are these 2? Is the original and this one the same? And so what you'll have to do, some of the times I don't want you to think, they're always going to be super easy. Sometimes it's hard to tell. In this case, this one's not too bad. You should be able to look at it and say, well, if it's the opposite of y and I'm taking the absolute value of it, that should be the same. Okay? Now, if you're not with me right now with reasoning, pick a number. Put 8 in there. The absolute value of a negative 8 is 8. Now, if I change it to the absolute value of a positive 8, it's still the same thing. Okay? So, this one should be equal, and it should have x-axis symmetry. And then you'll try the y-axis. And the y-axis is telling you to do negative x and a positive y. We're going to go back and write down the same problem. And we're going to put negative x where the x is and y where the y is. So we're basically not changing the y this time. We're putting this in here. You just got to get that table in your head as quickly as you can. Just keep looking at it until it's in your head. And the absolute value of a negative x is still the same as the positive version. So, because of that, this original problem and this is the same. So that would be yes. Now, to take a minute and actually graph on your graphing calculator, and you should do that, just to see if you're on the right track. If you know how to operate your calculator at this level, you should. If you graphed this into y1 and this into y2, I'm giving you a sketch here. Let me try that again. This is what you should get on your calculator screen. Something like that, okay? Alright, so let's see. I just said yes to x-axis symmetry. Does that make sense? Can I flip this from top to bottom and it land on this? According to the algebra, it says yes. The picture proves that. Secondly, does it have y-axis symmetry? Can I flip this and land here? And vice versa. Same deal at the bottom. And the answer is yes. Graphic approach, algebra test approach. Again, just be careful in the directions because I do change them on you, and I do want on your assignment that you make sure you show me everything on your own paper, show the work, and today is more focused on the algebra. Alright, last concept in this section is on even and odd, and the words and the difference between those. For a function to be even, the function's graph is symmetrical with respect to the y-axis. Even is for the y-axis. Even is for y-axis. Odd functions are functions whose graphs are symmetric with respect to the origin. So remember, origin is a single point. So this odd functions have point symmetry. That's just a different way to say it. Okay? So you need to know both. Even functions have line symmetry across the y-axis. Odd functions have point symmetry. There are lots of functions out there, to be honest, that are neither even or odd. Most functions fall into one of the categories, but there are some that don't. So just kind of throwing that out there. Look at example 1 on this screen. I have a parabola right now. If it's even, it must be symmetric to the y-axis. We can see as I drew that in there that this side would flip to this side. So this one looks like yes. Now I am going to continue just to kind of make sure that I'm drilling those vocab words in your head. Odd. Odd functions are actually functions that have point symmetry. So if we already know this one's even, but let's go with this for a minute. There's my point. Origin symmetry. If I were to pick up this graph and rotate it 180 degrees, it would look like this. It'd turn upside down. This graph doesn't land on top of itself, so this is no. Most of the time, if you say a function's even, then it can't be odd. Okay, now I have seen a couple exceptions to that, but for the most part, it's one or the other. Okay, second, in this picture, let's go with even, and let's test it. Even functions are symmetrical across the y-axis. Can I flip this over and it look like this? Fold it perfectly, and this part land on top of itself. Well, no, this piece would land up here. So that's not going to work, and I would say no for that one. Then I would see if it's odd. Now, if I get yes, I'm good to go. If I get no, then that just means that this graph is neither. So you do have to do both. Now you're going to pick this graph up, and you're going to rotate it 180. And this is the type I was talking about with calculator, like turning your calculator over or upside down. Also, I've had people in the past that draw pictures. If you can visualize it, awesome. If you have trouble with that, literally take your paper and turn it upside down and see if it looks like the same graph. Okay? In this case, it does, and this one is odd, and so we're good to go. Again, functions can be even, or they can be odd, or they can be neither. Okay. All right. So again, the learning targets in this entire section deals with point symmetry, line symmetry, and then last, even and odd functions.